Okay, let's go over Autumn 2019 Final number 4. That is the optimization problem, the max-min problem, probably the hard one on this test. And so basically we have a square pyramid. So the base is a square and the sides are isosceles triangles. And my picture here is not as good as the one that they have, so hopefully you can understand what's going on. But each side is an isosceles triangle, 4 sides, so it's base of the square. The square has sides x, and they decide to call the height of our isosceles triangle, of our pyramid, y. And we want to build such a pyramid where the volume is going to be 1/6, and then we're going to use meters, but it doesn't really matter, we'll just make sure everything is in meters. The volume is 1/6. We want the volume to be 1/6 meter cubed, and we want to figure out what height do we make this, and what width, what x do we need, and what y do we need to make this the smallest surface area for the triangles. We don't care about the base, but we only have so much material to make the sides. Maybe it's a tent, right? And you want to make your tent as light as possible, and with no floor to the tent. You want to make your tent as light as possible, or as little bit of material as possible, but still be able to fit 1/6 cubic meters inside it. That's the idea. Okay, so we're going to optimize the fabric to have as little fabric as possible. So first we need to know what the volume of one of these is, and it's not obvious, and they don't tell you in the test, so I'm assuming that they must have gone over these formulas, or maybe there's a formula on the top or something for the formula for a pyramid like this. It turns out it's just like a cone. The volume for one of these things is 1/3 the equivalent as if it was a rectangle, if it didn't come to a point. Just like a cone is 1/3. So it's 1/3 the base times the height. Just like a cone is 1/3 of a cylinder. So here it's 1/3 the equivalent thing. So the base is x squared and the height is y. Okay, that's the volume, 1/3 x squared y. And we want to minimize the area. So we need a formula for the area of like one of these triangles. So let's call the height of the triangle is this thing here. So let's call that h, this line down the middle of the triangle, and it's slanted, right? So we want to write h in terms of x and y. Well, the base of this little triangle here, so I'm going to draw that little triangle, this triangle inside here. So I'm going to draw that here, looks like this. And the height is y, this is the middle, the height of our the isosceles triangle, that's h. And the base is half of x, right? Because it goes from the middle to the outside, so this is x over 2. So h then is what we want. That's because the area of our triangle is 1/2 base times height. So the base is x. Here's this triangle, right? One of our isosceles triangles, and the height is what we want to know, this h. But we can figure out h from here. So h squared is, as h is hypotenuse, so it's just y squared plus x over 2 squared, or h is the square root of y squared plus x squared over 4. So the area of our triangle is 1/2, the base is x, the height is the square root of y squared plus x squared over 4. We want to find what a is the best a to minimize this. And actually there's 4 of them, right? Because there's 4 triangles. So actually the full area, and I'm going to write this down here now, the full area is 4 times that. Oh, no, okay, I guess I'll write it right here. This is our little side thing. Our full area then is 4 times this, because we have 4 sides. 4 times 1/2 is 2, so it's 2x times the square root of y squared plus x squared over 4. Okay, we want to take the derivative of this and set it equal to 0 to find the minimum. Right? We want to find what x value or y value gives us the minimum there. Problem is we have an x and a y in it, so we got to get rid of one of them. Since we have an x twice, it might be easiest to get rid of the y. So let's get rid of the y squared here, and we have to use this formula up here to get rid of the y squared. Okay, so I'm going to write that down here now. So we have 1/6 equals 1/3 x squared y, and we want y squared from this. So let's see, let's multiply the whole thing by 3 over x squared. that gets rid of the 3 here. That cancels out the 3, cancels out the x squared. So on the other side then we have 3 over 6x squared equals y. That's just 1/2. It's a 2. Square it. So y squared is 1 in the top, 2x squared in the bottom. That squared is 4x to the 4th. So y squared is 1 over 4x to the 4th. And we got to plug that into here. So now I'm going to write it down over here. So finally our a is equal to 2x times the square root of y squared, which is 1 over 4x to the 4th, plus x squared over 4. Okay, that is our area. We want to find what x value makes that the minimum. If we graph this, that'd be one way to do it, throw it on Desmo, so we want to find what x values makes this the smallest area, because we want to minimize the area, right? We want to minimize the area for these sides. And then once we find what x value, we can figure out the y value. Since y is, I should rewrite this, y is 1 over 2x squared, so y is 1 over 2x squared from this formula. So if we know the x, we can figure out the y value, which is what they want. They want both. Okay, so we got to take the derivative of this and set it equal to 0. But notice that looks like a mess because we have to use a product rule, the derivative of this times this plus this times that. I think it'd be easier if we put the 2x inside the square root right away and made it a 4x squared, right? Because the square root of 4x squared is 2x. If we put the 2x in the square root, we square this and put it inside the square root. So let's do that. So this is the same thing as the square root of 4x squared times 1 over 4x to the 4th plus x squared over 4, which is 4x squared. Notice the 4's cancel, which is really nice. The 4, both of them have 4 in the bottom, and we have a 4 in the top. X squared over x to the 4th becomes just a 1 over x squared. We have an x to the 4th in the bottom, x squared on top. The x to the 4th wins by 2. And x squared times x squared is plus x to the 4th. Okay, that is what our area is. This is much simpler than this. So in this case, what really makes this problem easier is seeing that we can put the 2x inside as 4x to this 4x squared, and then multiplying them, we get this. Now we can take the derivative. So dA dx, the root with respect to x, is, this is just the 1/2 power, so 1/2, all that stuff to the negative 1/2, to the negative 1/2, times the derivative of what's inside. Let's see, this is x to the negative 2, so that would be negative 2x to the negative 3, and then derivative x to the 4th is 4x to the 3rd. Okay, well that's pretty messy, so let's just rewrite that so we can wrap our brains around it. So dA dx, finally, the derivative is, this is on top, this one's negative, I'm going to put it second, so I'm going to write it like this. So 4x cubed minus, oh wait, I should have done this first. This 1/2 cancels out the 2, makes that a 1, and makes that a 2. So really I should say, okay, I'm going to cross this out so I don't use a pen. But the pen shows up so much better in this. So, okay. Half cancels out this 2 and that 4. This one's a positive 1, so I'm going to have on the top 2x to the 3rd minus, and this is 1 over x cubed, right, because x to the negative 3, 1 over x cubed divided by in the bottom, the half went away, and it's the square root in the bottom, right, negative 1/2 of 1 over x squared plus x to the 4th. So this is our derivative. We want to set that equal to 0. Okay, now for this to be 0, we have two places. The bottom can be infinity, and that's weird, right? We don't want x go to infinity because x can only be so big. So that part's not right. For the top, for this to be 0, the top has to be 0. Okay, so we can ignore the bottom when we set this equal to 0. So basically, and I'm going to need a new sheet of paper here, we set the top equal to 0 for this to be 0. So 2x cubed minus 1 over x cubed is equal to 0. Well, let's multiply everything by x cubed. 2x to the 6 minus 1 is equal to 0, or 2x to the 6 equals 1, or x to the 6 equals 1 over 2, or x is equal to 1/2 to the 1/6 power. Okay, now we know what to make our x. We make our x 1/2 to 1/6 power. So what is y? Y is 1 over 2x squared. So y is 1 over 2x squared. And now it's like, how do we write this the simplest way? Let's see, that's 1 over 2 times 1/2 to the 1/6, 1 over 6, 1 over 6 power squared, right? X squared, x is 1/2 to the 1/6. We multiply powers, so that's the same thing as 1 over 2 times 2/6, which is 1/3, 1/2 to the 1/3. Okay, and this is the algebra part. 2 is the same thing as 8 to the 1/3. 1/3 is the cube root, right? What times itself 3 times equals 8, and that's 2. So 2 is 8 to the 1/3 times 1/2 to the 1/3. Okay, if they're both to the 1/3 power, we can multiply them. So this is like 8 times 1/2 to the 1/3. So that's like 1 over 8 times 1/2 is 4. So that's 4 to the 1/3. Let's see, can we do that? Anything here? Okay, here's another thing we can do. 4 is 2 squared, so that's like 2 squared to the 1/3, right? Because 4 is 2 squared. Multiply powers, so that's like 1 over 2 to the 2/3, or we can write that as 2 to the negative 2/3. I'm trying to write it the way they had their answers, okay? So this is what y is. So if x is 1/2 to the 1/6, y is 2 to the negative 2/3 power. You could have stopped anywhere up here, and written it simpler. But this is, that's probably the simplest way, base to a power, to write it. I don't know, 1 over 2 to the 2/3 would work. Lots of ways to write it. But that's our answer. The values, if you want to have a volume of 1/6 and you want to have as little surface area as possible for the sides, the triangles, not worried about the base, then you make x this number and y that number. Now, they say justify the dimensions you found, give minimum surface area. How do we know this is a minimum, not a maximum? Maybe this is the most material use. How do you know that it's actually the x value right there, which is 1/2 to the 1/6? How do we know that's a minimum and that it's not a maximum? And the way you know, there's 2 ways to know. For a minimum, the second derivative is greater than 0, because it goes from negative to positive. It's changing in a positive way. So the rate of change of the derivative, which is the second derivative, is greater than 0 from it goes to negative to positive. Or you could find the slope, just plug in a number on this side of x and that side of x. So let's see, x is 1/2 1 to the 6, 1/2 to the 1/6 power, which is a tricky thing to figure out. So I'm going to do it on here. That's 0.5 y to the x, 1 divided by 6, and I get 0.89 about. So this thing here is about 0.89. So this value in the bottom here is about 0.89. So we can choose one a little bit bigger and a little bit less, plug it into our formula for the slope, and see if it's positive or negative. If it's negative one side, positive on the other side. If it's not, if it's starts off being positive on one side and negative on the other side, we know it's a maximum, which is not what we want. Or the other way to do it is to find the second derivative. Okay, so let's go back. This is our derivative right here. So we could take the second derivative, take the derivative of this, and see if it's positive or negative at 0.89, and that does not look like fun, right? We're going to have to use the quotient rule. Taking the derivative of this, not sure I want to go there. So probably what's easier in this case is x is 0.89 at the bottom, choosing a point, so here's 0.89, choosing a point on this side, like 1 1's a real easy value to put in. And choosing a point on the other side, we can't plug in 0 because we have a dividing by 0 in our derivative. Here's our derivative here. We have a 1 over x squared and 1 over x cubed. We can't plug in 0. But we can choose another number that's easy to plug in, like, I don't know, point. There's no real easy number if it's not 0. 1 is easy. So let's plug in 0.5 maybe. So 0.5. Okay, so we plug in 0.5 in a derivative, point in 1. If we plug in 0.5 and it's negative, and we plug in 1 and it's positive, we know it's a minimum. Now we really should do both, because what if it's one of these things? What if the slope is negative here, but also negative here? Then it's not a minimum. And it probably won't be, but we never know. So we got to do both sides. Okay, so again, our derivative, let me rewrite this, dA dx, why did I put two d's there, is 2x cubed minus 1 over x cubed divided by the square root of 1 over x squared plus 4. And that's our derivative. We want to know if it's, we know it's 0 at 0.89. If we plug in 0.89 here, we should get 0. But is it positive or negative 0.5? Now, the good thing is we can ignore the bottom. The bottom is always positive. Square roots are always positive. All we got to do is the top. Okay, so it's really not so bad. So let's do it for 0.5. So we have 2 times 0.5 cubed minus 1 over 0.5 cubed. That's not so bad. 0.5 squared times 0.5 is 0.125. So this is 2 times 0.125 divided minus 1 over 0.125. Let's see, this I can do in my head. That's 0.25. And 1 over 0.125 is 8, which is clearly negative, less than 0, which is good. That means that was what we want. For a minimum, we have to have the slope on the left side, the 0.5 less than 0. So this side here is less than 0. So that's good. Now we got to plug in 1 and hope it's greater than 0. Hope the slope is greater than 0. 1's easy to plug in. So plug in 1, we have 2 times, again, all we need is the top, because the bottom's always positive. 2 times 1 cubed minus 1 over 1 cubed. Well, that's just 2 minus 1. 1 cubed, that's a bad 3. 1 cubed is 1, right? 2 minus 1, which is 1, which is greater than 0. So here it's greater than 0. So here it's greater than 0, so sloping up, so it definitely is a minimum. So now we showed it's a minimum. They didn't show how to do this in their answers, but that's what you had to do for the last points. To show it's a minimum, we choose a point on either side, and it's got to be negative one side, positive on the other side. Or in this case, positive. Negative one side, positive on the other side to show it's a minimum. Okay, that was one of the hard problems. That was the max min or optimization problem from this test. So hopefully that makes sense.